Hello guys, so in this video I'm going to talk about the extrinsic camera matrix. So in the previous video we saw the intrinsic camera matrix. So the intrinsic camera matrix was just a, a small variation that we did in the camera model. So that was due to some problems that we faced. So that was that. Now let us see what is the extrinsic camera matrix. So intrinsic camera matrix is given the name because it is something internal to the camera. So that is something that the camera has to deal with. So there were some camera limitations in the previous time, or there is this particular thing that has nothing to do with the world coordinates or the image, how it is formed or something like that. This is something internal to the camera, this focal length or something. So all these things were internal to the camera. This is like camera properties, this focal length f or lambda, whatever. So this is the internal properties of the camera. So hence it is given the intrinsic matrix. So that is internal properties of the camera are shown by the intrinsic matrix. So we saw this homogeneous form in my previous video. So we could just extend that homogeneous form like this, and so what I have done is basically just taken this particular thing out. So this is what I have taken it out, and this is identity matrix that I formed over here. Why am I doing this will be clear in a bit. So this is the actual this particular thing is our intrinsic camera matrix, this matrix over here. So that is what we saw. This is the same matrix that I have over here, right? So that is the intrinsic matrix that I have. So I can so this is named as K. So let me name this as K. So this is a 3x3 matrix that I've taken sort of out. There is this identity matrix over here, and there is a zero matrix over here. So this is just a way to represent this particular thing. So this is, so this X bold C, this X bold C is nothing but this whole so this is X, Y and W, all small. So the camera coordinates are denoted by all small letters. So this is what we have over here. So this particular thing is XC, this particular thing is XW, this capital X, capital Y, capital Z, this is XW, and this particular thing is IO. I is an identity matrix 3x3, and O is a zero matrix or 0 matrix 3x1, and this over here. So this is the intrinsic matrix that we have. So now that is clear to us. Now if we see our camera model, so we saw that over here I have kept the world coordinates and the camera coordinates, that is this xy plane, coincide. That is, the capital X is equal to 0, which is nothing but this point, coincides with small x is equal to 0. So if you place a point, so this point in the image plane is exactly this thing. So please understand this, that the origin of the 3D world is mapped to the origin of the 2D world. So this is the assumption that we took while deriving these equations. But then this may or may not be true. There may be a possibility that suppose I have two cameras, I want to deal with two cameras. So there is one camera which is suppose say over here, and I am taking taking two views or something like that. So now if you see over here, now this has a different coordinate which is over here. So these equations may not work for this particular camera. So because of that, we will first need to align this particular location with this origin, which is we will need to align both the world coordinate and the camera coordinate, and that is exactly what the extrinsic matrix is going to do. So let us see. So here we have the extrinsic matrix. So here we have the model, extrinsic camera matrix model. So basically this is like this. Suppose these are my 3D coordinate systems, that is the 3D world coordinate, 3D world. So capital X, capital Y, capital Z, these are nothing but my 3D world coordinates, and this small x, small y and small z are my camera coordinates. So this is camera coordinates, this is the 3D world coordinates. So you might be wondering why Z for the camera coordinates. So this is just for now. We will so it is basically to align both these axes. So this particular thing has a Z over here, a small z, but just that we ignore it because it is of no use. So this z that is over here is just a dummy sort of variable, because this image will not have any content of z. So that is just why I have written z. So please do not get confused about why this z is over here for the camera coordinates. That is anyways going to be eliminated afterwards in the intrinsic matrix basically. So now this is the scene. I have my camera over here with these coordinates as the axis, and the world scene origin, so whatever this is my world, the 3D world, its origin I have kept over here with these alignment of the axis. So now my point is to first transfer this point to this point. So I need to just move this over here. So we know that how, so like we moved this origin to the over here in the intrinsic camera matrix. Now we will have to move this particular origin over here. So that is what we are going to do. So this is also one of the translation. So because we are moving the whole plane from here to here, we are translating this particular axis, right? So suppose that this particular point with respect to the 3D world, so if you say this as 0, 0, 0, then let me say this as capital C, where capital C is nothing but a vector which is some cx, cy, cz, which is nothing but the coordinates of this particular axis. So to be more clear, this particular point is nothing but cz, this point over here is cx, and the y particular thing, the more it is in the y direction, so that particular thing over here is cy. So I hope you get the idea. So this is cx, cy, cz, and this whole vector I am denoting as capital C. Okay, so this is C, and suppose I have any other point xw. So this is my say any point in the 3D world xw, and this xw is also a vector. So this xw has x, say capital X, capital Y, capital Z. So this has these three coordinates, where this point is capital Z. So this point is capital Z, this point is capital X, and capital Y, and the story. So this is xw. So this is a point in the 3D world, right? This is my 3D world, and this is a point in the 3D world. Now what I need to do is basically I need to see this particular point with respect to the camera coordinates. That is my task. So that is what I mean by putting this over here in the origin, at the origin, because that is important, because I need these both to be aligned so that I can use this particular thing that we discussed in the previous video, this camera model, this intrinsic matrix, and the story. So this is what we can use. So in order to have this particular translation or transformation, we will need to do this. So what is this? So I have, say, some xc dash. So this xc dash is nothing but the same point. So let me write it with, suppose, pen. So the same point is now denoted at xc dash. Just the difference is that this xc dash has c as 0. So if you consider this as 0, 0, 0, then with respect to this axis, this point is xc dash. So that is what. So to give a better picture, this coordinate over here is going to be some, say, xc dash y. Then say let me project it like this. So this point over here is x, c dash x and xc dash z. So I hope you understand. So what I am doing is, so there was this xw that we had. Now this xw was respect to this origin 0 comma 0 comma 0. So now by using this particular equation, what happens is I get an xc dash. Now xc dash has coordinates, so basically this xc dash is with respect to this origin. So this is like a shift of origin, which you can do with this particular way. So I hope and this is understood to you. So this is the basic step of going to the extrinsic camera matrix. So we had our camera over here and the 3D world was arranged accordingly. Now we have arranged everything according to the we have aligned both the 3D world and camera matrix, camera coordinates, sorry. So we will get when we do this particular transform, we will get something like this. So where this is my, say, x, this is my capital Z, so this is my Z and this is my Y, and over here this is my x, this is my Z. Oops, this is okay. Oh, so a mistake over here, this is Z and this is Y. Whereas you could have any, you could take this also Z, because we are anyways going to rotate this. So this is what we have. So this is small y, please understand, this is small y, this is small z, and this is capital Z. So please note that capitals are for all the 3D world coordinates and small letters are for the camera coordinates. So anywhere you see camera coordinates, that will be in small letters and the 3D world will be in capital letters. So this is now what we have. When you translate this to over here, that is what we have. So now you can see that these axes are still not aligned, so these need to be aligned. So for that, what we are going to use is a rotation matrix. So now this rotation matrix is going to be different from the rotation that we learned in the initial lecture, or the first lecture basically. So this is different because this is in 3D, because if suppose this is my hand, so this is a 3D object. Now I can rotate my hand like this in this direction, I can rotate it in this direction, and I can also rotate it in this direction. So there are 3 ways possible. So in 3D you get 3 different rotation matrix which you can rotate in any in 3D basically. So these rotation matrices you can see over here, this is what the rotation matrices would be. So rotation in X, rotation in Y, rotation in Z. So this you can derive similarly as we derived for the 2D case. So accordingly you will get a rotation matrix to basically map both of these axes. So now if suppose you have this as your what we say, the present input is this, and you want your output to be this, so you need to transform it to a rotation matrix. So after transforming it to a rotation matrix, we will get exactly aligned coordinates. So this is what we are going to get after this transform. So let us see what have we done. So first the camera matrices were like the coordinates were like this. This was the camera coordinate, this was the world coordinate. Now first I translated it over here with this particular transform. So I am just taking, so this was my input and my output will be this. So I will put my input over here and I will get output x dash xc dash. Next over here, this thing is basically my input, so that is xc dash, this is my input, and after transforming it by a rotation matrix, what I am going to do is I am going to get this aligned output. So that is what I have done basically. And so xc dash over here, so xc dash is nothing but I hope you can see this. Yeah, so xc dash is equal to xw minus xc, so that I have placed over here, and there is this rotation matrix. So just to give you a right picture, so there is this xc which is a vector, which has small xc, small yc, small zc, this is equal to rotation matrix, which is over here, xw, which is also a vector, xw, yw, zw. So this xw was nothing but this particular thing. Xc will be after alignment. So after this matrix is come over here, after it is aligned, so what is the same point, xw will look differently, because now I am with respect to this axis, it is right. So that is what is xc over here. So that is, so this is basically what with respect to what. So I hope that is clear to you. If not, I can give you a simple example. So let us go in 2D. So now this point is 0 comma 0, but the same thing for this matrix, this may be say 5 comma 5. So if suppose this is say 10 pixels long, this is 10 pixels long, so with respect to this origin, this 0 comma 0, this is 5 comma 5, but with respect to this origin, this the same point is 0 comma 0. So that is the same thing that we are doing. This point over here, xw, with respect to this 0 comma 0 comma 0 is xw, which is capital X, capital Y, capital Z. And now with respect to this coordinates and aligned according to this will be some something. So that is what we are finding out. So that is our xc basically. So this is what we have got now, and just now converting this to a homogeneous coordinate thing. So now this was all xc, yc, zc. So now I am converting this to homogeneous. I am just adding a 1 extra over here. So this you will see why this is also important. And similarly I am putting in x, y, c over here. I am xw, yw, zw, I am just putting a 1 over here and multiplying this. So I have just multiplied it over here. And now this particular thing, so you understand why I have added this zeros over here, zeros and ones over here. So that is just to equate the matrices, right? So that is what we have done over here. And now next what we are going to do is we are going to compress this so that it looks nice. So this is just for a small interpretation. So in the literature, many places you will find this particular format of the extrinsic camera matrix. So the format is as follows. So this xc, yc, zc are nothing but xc over here. So that this particular thing was nothing but xc, my actual vector, camera vector. So this is my actual vector, camera vector. Similarly, this is my actual vector xw. So this is xc, this is xw. So this much is xc, which I have written over here, that is a 3x1 vector. This much is xw that I have written over here, and there is a 1 that is written over here and there over here. So if you see this much is c, x, cx, cy, cz. This much is c, and this is 1. So if you see what happens over here is I'll just, so this is the compact form that I have written over here. So if you see xc1, I am just opening this up. So xc, this thing is nothing but r into xw 3x1 minus rc. So that is what I have written over here, and this thing is the same thing that is over here, if you see. So this particular thing is the same thing that is over here. So xc 3x1 is this xc 3x1, then this r 3x3 is this r 3x3, then this xw 3x1 is this xw 3x1 minus r. So this is like in brackets because this is xw minus c, so minus r into c. So that is what we get, and then this is like a dummy thing because of homogeneous things. So this 1 is nothing but 0 into x plus 1. So that is what we have over here. So this is just to add this homogeneous coordinates over here, which is what we are. So we are basically unifying everything into homogeneous coordinates because it makes life easy. So that is all about extrinsic camera matrix. So this particular matrix that you get is our extrinsic camera matrix, and you remember that this particular matrix that we get is our intrinsic camera matrix. So just a quick difference between the two so that you don't get confused. So an intrinsic camera matrix transforms 3D to 2D. So for intrinsic camera matrix, the input is 3D. So you can see over here for input for intrinsic camera matrix. So this is like the equation. So the input is 3D, that is capital X, capital Y, capital Z, and a 1, that is homogeneous coordinates. And you can see the output is 2D, small x, small y, and a W. So this is homogeneous, right? So because of that there is this W. Small x, small y, W. So this output is 2D. So you give a 3D kind of a thing over here, you get a 2D output over here. So that is what intrinsic camera matrix is going to do for you, 3D to 2D. But if you see an extrinsic camera matrix, it takes input 3D and output also is 3D, because it is just doing this. It is taking this 3D input over here, XW, and doing some transformation so it can convert it to XC. What is XC? It is that aligned sort of thing that we have. So that is the difference between intrinsic and extrinsic matrix. So I hope things are clear. Thank you so much for watching my video. Thank you so much.